you know, if we can show that it is a group, of course. Okay, so we talk about a direct product group. Right here is a direct. So, so here we have all ordered pairs of this element belongs to G1 and this element belongs to G2. Okay, so there's a direct product of two groups, and if you want to think of them as sets, because groups are special kinds of sets, then that's a Cartesian product. All right? Okay. Now, so you have this set here of all ordered pairs. Now, a set is to form a group. A set alone is not enough. Right? A group is always like a duo. It has two things. It has a set, and it has a binary operator operating on that set. That is, you know, the four properties: closed, associative. There's a unit belonging to the set, and there for each element of the set there's an inverse. And if all four are true, then your set is a group. Well, your set and the binary operator is a group. Okay. So for this set of ordered pairs, we need to define some kind of binary operator on that set. So what could we do? Like here's one element of this set. Right? It's of this general form. Okay? And here's another element of this set. So we have two random elements of this set. Okay? And here's the binary operator on it. So we want to define, that's why I've got 3 bars here by definition. We want to define a binary operator on these two elements that sort of makes sense, that we can make a group out of. So how do you go about doing that? Well, with a bit of thought, you end up with something like this. Okay. So I'm just not just throwing it at you, and we can prove that it is a group. And so this direct product you can call a group. If we can prove that this is a group, you can call this thing a direct product group. Right? All right. So here's the definition. So this and this are two random elements of this set. It's still a set for the moment. We haven't proved it's a group yet. Okay? So what you do is you take this. You take the first one of your first element of this, and you take the first one of the second element of this. You take these two, and you perform the binary operator of this one. See, these are two groups. They might have different binary operators. Like this one's binary operator might be a little circle, and this one's binary operator I might represent as a square or something. Yeah, just it might be a different binary operation. Okay, so. So I take this one, and I perform this binary operation taken from G1 on these two, because these two are both from G1. Right? That's from G1, that's from G1. Right? And the second one here, I take this and this, they're both from G2 here. Okay? And I use the binary operator of this one, so represented by a little square, okay, here. And I binary operate that with that using the second binary operator. That's it. So that like those two lines there are like the heart of this lecture. It's because that gives the definition of what the binary operation is on this product set. Right? So really remember those two lines. Okay, let's do an example. We're trying to show that using this binary operation, on this set, the set of ordered pairs, gives you a group. So let's start with, and now let's using this definition of a binary operation here. Let's let's create a group table, because from the group table you can start seeing possible inverses and the unit and closure and associativity and all that stuff. Let's do an example of a group table. On what group? Well, let's take the direct product of these two groups. Okay, Z2. Here it is here. And what is Z2? It's just this very simple group, just two elements of order 2. Now the group order is 2, just has two members, 0, 1, right? Now the product, well, we're going to call it a direct product or a Cartesian product. We're not quite sure it's a group yet. Okay, well, let's call it a Cartesian product for the moment. Now you Cartesian product these two sets, you get that. Okay, so they're the four members of this. Right? Now we're constructing a binary operations table, which we hope will become a group table. We're trying to prove that. Okay, so the binary operator on this set will that be plus mod 2. Okay, and we will use the same binary operation well, they're the same group, right? They're both the same group. So this and this in this case are the same, right? We just add mod 2, right? So here are the four. Here are your four members. Here they are again. And then you apply this rule, and this binary operator here, it's the same in these two cases, is you just add mod 2, right? All right. So we take that and that. So this would be this one, and this, and then this is this one. So naught here. So that way naught plus naught gives you naught, and that with that. So naught plus naught gives you naught. So now, in fact, this is the unit, right? See, so this will be the same as this one, and that's the unit. So this column will be the same. All right, let's try this one. So 0, 1 goes here. So 0, 1 times 0, 1, 0, 1. So 0, 1, 0, 1. So 0, 0 is this. That must be 0. And 1, 1, and you're adding, remember? So 1 plus 1 is 2, mod 2 is 0. So you get the noughts as 0, and 1 plus 1 is 2, mod 2 is 0, so you get a 0 here. Okay. Now similarly, well, let's do one or two more. All right. Well, let's try this one. So the 0 and the 1 you add, so you get 1. The 1 and the 1 you add, that's here. That's 2. Mod 2 is 0, so you get a 0 here, and so on. All right. So that's your table. Now it's closed. Let's start proving that it's a group, and I think I'll stop here for the moment, clean the board, and then we'll prove that with this definition, this binary operation on this set, that it's actually a group. So it satisfies the four properties. So we have to show closure, we have to show associativity, we have to show there's a unit, and we have to show for each element there's an inverse. So we'll prove that in the next part.